I'm Jacob from the Cedar Rapids Public Library, and today you're watching the inaugural episode of Adventures in Science, where I will attempt and explain various scientific experiments with varying degrees of success. Because if there's one thing you need to know about science, is sometimes it's more art than science. I'm going to start off today by showing you a bit about surface tension. Surface tension is caused by the attraction between liquid molecules. Different molecules have different levels of attraction. And today, we will mostly be dealing with water, which is held together by hydrogen bonds, which in water's case means that they are constantly pulling themselves as close together as possible to take up as little surface area as possible. You can see this demonstrated by when we keep adding water to this penny. Despite how much it seems to be edging towards overflowing, it seems more interested in itself than overflowing, at least until the point that it eventually does. Now this happens because the surface area of the molecules at the surface of the water have nothing outside to bond with, and so instead are attracted to the interior molecules of water. This pulls the exposed molecules together tightly, and it creates a sort of film-like surface over the exposed sides of the water that is able to keep things much denser than the water itself. An example being something like this pop tab, which, while denser than water, when submerged, is not heavy enough to break the surface tension of the water. The amount of weight required to break surface tension varies depending on temperature, with surface temperature generally increasing with cooler water and decreasing with warmer water. Now that you understand a bit about surface tension, if you're anything like me, you're wondering, are there any fun ways to mess with it? And the answer is very much yes. And if you're not like me, and you didn't think that, no worries, I thought it for both of us, it's fine. So here we have a bowl filled with water. Next, I'm going to grind up some peppercorn in here because who doesn't enjoy lukewarm water with a zesty crunch? Great, now that we've ruined this perfectly fine water, you'll notice that some of the peppercorns have sunk to the bottom of the bowl, while the smaller bits are actually floating on the surface. If you're thinking this is because of the surface tension that we discussed moments ago, you're correct. But watch what happens when we take a Q-tip covered in a bit of dish soap and put it in the center of the bowl. While at first glance it may seem like these pieces of peppercorn have all collectively realized that they left the oven on at their house, or that maybe they have just a pathological fear of ever being clean, what actually is happening is much simpler and far less strange. Every molecule of dish soap has two ends that attach to two very different things. One side is what's considered hydrophilic, which means it's attracted to water and binds with molecules of water, thereby weakening the surface tension. But the water molecules want to keep their surface tension, so they are pulling back away from the soap, looking for more of the hydrogen bonds that kept them together in the first place. The other end of the dish soap is the opposite and is known as hydrophobic, which means it's not attracted to water, but will often readily mix with fats and oils. In order to get a better look of that kind of interaction, we're going to try a similar experiment using milk. Now, milk is about 86% water, depending on the type of milk you buy. The other 14% is largely made of fats, proteins, minerals, all the stuff you see on the nutritional label when you've already solved all the puzzles in the back of the cereal box. And because we aren't just looking at reactions with the surface tension, but the fat content as well, we're going to have to use something a little easier to track, food coloring. Okay, so now we've got some 2% milk here, and I'm going to carefully add a few drops of food coloring. There's one. And there's the other. Then what we're going to do is we're going to take a little bit of dish soap, again attached to a Q-tip, and put it right there in the center. You can kind of see everything, well, kind of spreading out a bit, but I mean, it's beautiful, gorgeous even, but I honestly can't tell how much of that is like surface tension or how much of it is the fat molecules.
This is Adventures in Science, not Adventures in Guesswork. I demand more data.
All right, I have 4 different bowls containing 50 milliliters of skim, 1%, 2%, and whole milk. I've let each one stand for at least 1 minute before adding a couple drops of red, green, and blue food coloring.
By observing them in ascending order of fattiness, we will count how many times we can add dish soap before the reactions stop happening.
All right, so first up is the skim milk. Let's see how many pokes it takes to get done with this one. 1, 2, 3. Now this is our 1%. 1, 2, 3. All right, next we have 2%. 1, 3. All right, and this is the whole milk. 2, 3. Okay, so that one, but it's skim with 9, 1% with an astonishing 28, 2% with only 15, and then whole with 25, which doesn't make any sense. So I think what we're going to do next time is we're going to do it all again, and this time I am going to try to spread out the food coloring a little bit more. This one is skim. Again. 1, 2, 3. Okay, here we have the 1%. 1, 2, 3. And here we have 2%. Again. 1, 2, 3. Okay. Now this is whole milk. Again. 1, 2, 3. Okay, so after round 2, we've got skim with 10, 1% with 23, 2% again with 15, and whole with an astonishingly higher 36.
So, here's a list of our outcomes, which are different than what I expected. The main takeaway seems to be that 1% is clearly the superior milk, so remember that the next time you go shopping. While we didn't get the answers that I was expecting at the very least, it does offer us some different questions. Was the dish soap less effective the more it was dipped in the milk using the same Q-tip? Possible. Was the surface tension forcing the larger fat molecules into corners I wasn't exposing to dish soap? Probably. Are the chemical reactions happening here more complicated than soap binding with water and fat molecules? Absolutely. Science is a process, and there are 100 ways to more deeply explore how these reactions work. Unfortunately, I ran out of bowls, so I will leave the better science up to you.
Thank you again for taking the time to join me, and I hope you'll do so again next week when we are going to, let me look at the schedule here. Oh, explode some lemons. Huh, neat.